Good afternoon, everyone. On behalf of all of us at the National Glass Association, thank you for making time in your day to join us for Thirsty Thursday, featuring NGA's own energy code consultant, Tom Culp. In this final webinar of the year, he'll summarize the advancements in glazing technology, fenestration performance, and energy codes we've seen this year and what to expect in the coming months. Registration is open for the upcoming NGA Glass Conference Miramar Beach, which is near Destin, Florida. Conversations will focus on all the ways glass products are progressing and evolving in the building code space, legislative space, and of course, the technical space. You can also count on the same festivities typical of our winter conference, including the member celebration dinner, fun run and walk, and golf scramble. Early bird rates end after December 13th, so don't delay signing up. In addition, spouse registration is free, so we hope you bring your partner and plan to stay a while. This March, as the Building Envelope Contractors Conference will celebrate its 25th anniversary, returning to Las Vegas where it all began. Attendee registration will open January 11th, and we hope you'll make plans to join us. This course is accredited by NGA for 1 hour of AIA HSW credit. Learning assessments for AIA credit and certificates of completion are available upon request. Simply email sarah@glass.org as listed on the screen. I'm now pleased to introduce our speaker. Dr. Tom Culp is the owner of Birch Point Consulting. After earning a PhD in chemical engineering from the University of Wisconsin, Dr. Culp has spent the last 21 years in the glass and window industry in the areas of energy efficient glazing and window performance, LowE glass coatings, and building code development. He is co-vice chair of the ASHRAE 90.1 Standards Committee and is an active participant in the International Code Council development hearing process. He serves as the Energy and Green Construction Code consultant for the Aluminum Extruders Council, NGA, and our own Glazing Industry Code Committee. Tom, welcome.
All right, thank you, Sarah. So today, as Sarah mentioned, we'll be kind of going through what I'm calling recent advancements in glazing technology, fenestration, and energy codes. For those of you who may already have attended like some of NGA's meetings, this may not be necessarily new information, but this is really aimed at architects, specifiers, designers, and also those new to the industry. So we hope it's kind of a somewhat introductory, but also a glimpse at what's new and coming down the road. As Sarah mentioned, this is a AIA accredited course. So it's designed to focus for architects and designers about what's up and coming in the energy codes as well as technology. And we also address retrofitting existing buildings, which is a new topic that's up and coming. So some of the learning objectives at the end of the session, participants will be able to describe new glazing and fenestration technologies, just classify how different types of fenestration are treated in the energy codes, which is a little different sometimes in the building code, identify which component features are required to comply with the newest energy codes, learn a little bit about and identify how to address thermal bridging when it comes to fenestration, and then also looking at discussing and describing new glazing technologies for retrofitting existing buildings. And since this is an AIA course, we'll be going a little bit longer than our normal half hour, since this is accredited for 1 hour. I'll try and go through some of the parts somewhat quickly, though. So first, let's just back up and look at windows over time. If you go way back, in the medieval times, you have what do you have? Small windows, no glass or single pane glass at best. Oftentimes just tapestries covering the windows. And then let's jump ahead several hundred years to the 1950s and 60s. And what has changed? Honestly, not that much. It's, you look at buildings from that kind of brutal period, you have small window area, mostly single pane glass, some clear glass or tints. But honestly, how different are those? Not a lot. But then let's go ahead another decade or two, and all of a sudden you see a huge change. Now all of a sudden you have these large window area, these kind of reflective glass boxes, mostly, but again, really not as much has changed in terms of energy performance. It's mostly single pane, non-thermal frames. The big difference is, of course, now you're seeing curtain wall construction where the engineering has progressed, where we can, from a structural and installation standpoint, do a building like this. But let's go to today. So what do we see now? We're still seeing large window area. There's a reason for that. Daylight views, health impacts, things like that. But the difference is now that you can do a high performance facade with advanced LowE coatings, double or triple glazing, advanced framing, and we'll talk about some of that today. But again, this is a good point to remind ourselves, why do we have windows? And really, it's the human aspect. We design buildings for humans. We don't design them just to, sit in a cave. There's the human aspect, occupant health and well-being. And there's a number of studies that have been done over the years showing having access to daylighting and quality views produces better learning, faster healing, higher productivity, higher value. And some of the examples are shown there where you see better test scores in students. You see increased retail productivity. Workers are more productive. Absenteeism is less. In the healthcare settings, you see decreased use of medicine. You see decreased hospital stays, which is also has a financial impact as well as obviously being beneficial to the patient. You see increased retention of nurses and healthcare workers, things like that. So it's really pretty dramatic, and it's just a good reminder of, yes, there's a reason to have windows. Yes, there's a reason to have daylight and views. But then how can we make that a high performance facade at the same time? And there's some resources that NGA has that has a lot of this information. So what's new in glazing and fenestration technology? So first, let's think about nanotechnology. And you're looking at one of the first uses of nanotechnology in the world. And although it's actually not new, and it's not the clouds, it's the glass that you're looking through. Everyone thinks about microchips and things like that. But guess what? LowE coatings are one of the first widespread uses of nanotechnology. And here's an example. So this is, you hopefully know about LowE coatings and LowE glass. And what we have are on the screen here, this is one of the newer technologies. This is a triple silver LowE coating. And the LowE coatings are basically, they have a transparent microscopic coating which reflects infrared heat. It's a fancy way of saying it helps to reflect the heat back into your home. And it actually is a nanotechnology. The one technology on the right has 3 silver layers. That's why it's called the triple silver. Each layer is like, in the rough range of 10 nanometers. Then there's up to like 15 or, many more layers of other materials in there to make the overall coating work, but also be transparent. So what's this do for us? It reduces the radiative heat loss, which then reduces the U factor, makes it more insulating overall. On top of that, LowE coatings, I've often heard, are for solar control. And yes and no, but it's good to remind people that the main purpose of LowE glass and LowE coatings is to reduce the U factor, reduce heat transfer. But on top of that, you can tune all those layers in there to control solar heat gain, either high, medium, or low, whatever you need for that particular building. So it's kind of serving dual purposes in that circumstance. So when I do this presentation in person, I'll often ask the audience, so how many glazing products would you guess there are? Thinking about, yeah, there's some different kinds of tints. There's clear and tinted. There's LowE coatings. There's other kind of things like that. But how many would you guess? The answer is thousands. And usually the number of people say, oh, I don't know, 10, 15, 20. No, it's thousands. This is the International Glazing Database, which is one place that it's administered by Lawrence Berkeley National Lab. And it's a way of visually showing, all the different glazing products in there. And you have clear, ultra clear, low iron glasses, tints, LowE coatings, reflective coatings, dynamic products, laminates, films, and it's not just one or two. There's thousands. So it's give you an idea of the range of technology that's in glazing today. So what are some of the newer types? So there's a wide range of LowE coating types. It's not just LowE. There's LowE in every range of solar heat gain. SHGC is solar heat gain coefficient. from high passive solar for cold climates to very low solar control for hot climates. So it can be tuned for what you need in northern Minnesota or southern Arizona. I've showed that picture of a triple silver. It has 3 silver layers in it, and it's designed to give low solar heat gain, good solar control, as well as low U factor for the southern climates. And then there's a new generation triple silver, which has even lower solar heat gain. So you'll see that available as well. There's, again, with this wide range of technology, you can have colors or color neutral, and you'll see all of the above available when you look into the marketplace. And then the other new trend we've seen is, for a while, it's all about high transparency. And then now that seems to be kind of going back a little bit, where it's really up to you guys, the designers and architects. What do you like? And so there's a certain amount of design reflectivity where it's either some people want a very strong reflectivity, especially places like in the Middle East, but others want no reflectivity, high transparency. And then there's a new kind of a set of coatings out there that kind of give mild reflectivity to try and strike a balance between. What else is out there? Dynamic glazing. Hopefully you've heard about this by now. Dynamic glazing just means it has the ability to change its products or its properties. It's not just the same solar heat gain and visible light transmittance all the time. It can change. And the most common are electrochromic or thermochromic glazing that can reversibly change its properties to optimize energy performance and glare control by the hour, the day, the season. It can be controlled by photosensors, occupancy sensors, time scheduling, or even just manual controls. Where you see the solar heat gain can vary in the same product throughout the day from about the range I typically see is from about 0.09 up to 0.47 or so. The VT, the visible light transmittance, similarly can range even a little farther from about 0.02 to give very good glare control, all the way up to transparent coating, like a 0.62 range. So a wide range of control. I will note that privacy glass should be viewed differently. You may have seen this. It's usually used on the interior, like in office spaces and so forth, where you flip a switch and it'll turn from kind of clear to a white or other colors. And it's more for privacy. That actually doesn't have much impact on solar heat gain. So it's usually not used on the exterior of the building. It's more changing it from a transparent to a scattered translucent look. So in my mind, I consider dynamic glazing and privacy glass as separate products. Dynamic glazing, here's an example of what it looks like. So it's still transparent in all cases. It's just changing that tint so that you can change the solar heat gain and visible light transmittance from clear to kind of a darker color. What else will you see out there in the design world? There's some new configurations. It's, the most common, of course, is just 2 panes with a single LowE coating on the number 2 surface. That's the configuration on the left, where you see the LowE coating there with indicated as a blue dotted line. That's the most common. The center of glass U factor will be about 0.24 in IP or US units, and that's with argon. But there are new configurations that you should be seeing or specifying. The next step to the right, or on the left side of the next one over, is where you have 2 LowE coatings and what's called a 4th surface or a room side LowE coating. So we typically number the surfaces from the outside in. So 1, 2, 3, 4. So in that case, you have a traditional LowE on the number 2 surface, but you can also have a durable LowE on the number 4 surface. It's exposed in the interior of the room. It's being touched, it's cleaned, exposed to humidity. So it needs to be durable. And there are durable LowE coatings of different technologies out there and available. The advantage is, what's that do for you? Now you get a U factor of about 0.20, which is getting close to what triple pane is with a single LowE. That's the next item over, where you see U center of glass is 0.18, where you have triple glazing with 1 LowE coating. So you can get almost the same performance, but with in double glazing package. So that's provide some cost benefits as well as more flexibility in the frame and so forth. But of course, what you can do with triple glazing gives you flexibility because you have more surfaces, more places you can do things. So you can add on the far right, add 2 LowE coatings. Most traditional place is number 2 and the number 5 surfaces, although you can do other things as well. And then now you're all of a sudden your U factor for the glass only is dropping down to the 0.12, so very high performance. The other one I want to mention that you may have heard about out there are thin triples. So this is triple glazing. It's just another form of triple glazing with no difference in that aspect, but they're called, what is different is they call it thin triple because it has you using a lighter weight thin glass in the middle. Now, the example shown there on the screen is kind of the ultimate where it's, in this case, you're having the thin glass is as thin as 0.7 millimeters, although it's probably more common to use around 1 or 1.2 millimeter. So it's very thin and you can narrow the gaps. So that whole triple glaze package fits in the same width as a double glaze package. That means you don't have to change the frame. So you can put that triple glazing performance in a good thermally broken or a non-metal type double glazing frame system. Now, when you do that, when you use those narrow gaps, you need to optimize the gas mix. So you use either krypton or a mix of argon and krypton to optimize the performance with those narrower gaps. So this is what's kind of, you may have heard about in the residential world as a thin triple. There's also some companies exploring thin triples on the commercial side where maybe not going down to the point, the 1 millimeter in the middle, but they're using like traditional 1/4 inch or 6 millimeter glass on the outer lights, but then in the middle, they're just using like a 2 millimeter or even down to 1.6 millimeter glass in the middle. And it's the same idea. It's thinner than what's normal, and you can kind of get triple glazing performance in a little narrower frame or narrower glazing package. What else will you see out there? Vacuum glazing. I hope you've heard of this, if not seen it. This is a dramatic improvement. Now we can go lower that typical 0.24 U factor, again, talking center of glass, double glazed unit down to 0.1. This is where you have 2 lights of glass separated by a very thin gap of vacuum, 0.2 to 0.3 millimeters. It's a vacuum, so it doesn't need to be very large. And in fact, it's a little easier to do when it's narrow, and because you also need to put in these support pillars because there's a vacuum. You don't want it to collapse onto each other and touch. And you include a LowE coating. So if you think back to your physics, it's a vacuum, so there's no convection. There's a LowE coating, so there's no radiation, and the conduction is minimized through the glass, and then by keeping those pillars small and the edge design is done properly. So you get very high performance. And the nice, interesting thing is it can range, the products out there range from about a little more than 6 millimeters up to about 8.3 millimeters. That's thin enough. You can often use it to replace single glazing. So it's a very interesting product for historic applications, like the product shown, or the picture shown on the right, where they took a single pane historic building. They didn't want to change out. The building owner either did not want to or could not change the overall windows because of historic covenants, so they or restrictions. So they swapped out and put in VIG in there and get very high performance. You can even get lower U factor when you combine it in a hybrid unit. So think of this as like a traditional IG unit, but one of the 2 lights is vacuum glazing. So you have a vacuum glazing plus a spacer, and then another LowE or another coating. You get very low U factor, very high performance. So hopefully you see that, start to explore that as a designer or specifier. Look for that if you can use that in your projects. Other new thing in the glazing side is glazing for on-site renewable energy production. ASHRAE 90.1 and it looks like IECC are both going to be requiring on-site renewable energy in new buildings, and so you can put it anywhere you want. You can so yes, you can do rooftop glazing. But BIPV is coming on, where you can use photovoltaics, solar production in lots of places. You can put it in overhead glazing. You can, like the lower left is a walkway in Salt Lake City where they're using it in the glazing over a walkway canopy. You can put it in sunshades, you can put it in opaque spandrel area. Everything you see on the screen here is photovoltaics generating electricity. There's even vision glazing now, where the two pictures on the right show clear, transparent glazing that is producing electricity. It's using the UV and the infrared parts of the spectrum to make electricity. And you now have the opportunity to put this on all your south facing, or even other, to other east and west orientations as well, and use all that glass area to generate power. So it's an interesting new technology coming up. So we've talked a lot about glass. What about framing? What's new in framing? So first, we're talking commercial here for the most part. So 90% of commercial framing, commercial fenestration uses aluminum framing. That's out of all the market studies. And there's a reason for that. It's from structural performance, durability, ability to do wide spans with narrow sight lines, design flexibility with like custom profiles and things like that, as well as like the recyclability and sustainability aspects of aluminum. But we all know aluminum as a material has high thermal conductivity. So so-called unbroken aluminum frames, do not perform well from a energy efficiency standpoint. So what do we know? This has been around for decades, but use a low conductivity material to break that heat loss path while still maintaining the high structural performance. And these are known as thermal barriers. So I'm sure you've used these, seen these. I do want to talk about terminology. There's thermally improved and thermally separated. You need to be careful. That's different than thermally broken. And NFRC and other places basically draw the distinction at a non-metal material with a greater or less than a 1/4 inch. So basically older curtain walls where you just have kind of like a little thermal isolator, that's thermally improved or thermally separated. That's not a full thermal break. A full thermal break has a wider separation with a non-metal structural material. There's a lot of technologies out there that some of the terms you may see: polyamide struts, pour into bridge polyurethane, fiberglass, double thermal barriers. And then we can also combine that with non-metal pressure plates in more complex shapes. So pictures help. So here's some of the technology out there. And again, I just want to stress, this is not just your basic thermal isolator on the bolt or 1/4 inch separators. It's at least a full thermal break is kind of what I consider standard performance. And then some of the newer technology coming out, you can see on the screen, it's a double pour into bridge, like on the left, and the circle with the yellow, you see 2 thermal breaks in series there. You can have complex shapes or use fiberglass inserts, like you've seen in some of the other photos. You can use fiberglass or polyamide pressure plates on a curtain wall to again improve the thermal performance. And that's an easy swap out. That's an easy thing to do, because installation is basically just the same, yet you're getting better thermal performance. So what about the energy codes, which is that's more of my specialty area. I work on the committees that develop the energy codes. What's happening for fenestration there? First of all, the overall code, the overall stringency in the codes, this should not surprise you. This, this is a graph showing, developed by PNNL, kind of showing Pacific Northwest National Lab, showing that how the code's stringency has changed over time. So if they just put 1975 as the benchmark, it shows where are we at. And you look where we're at, the late 2019, ASHRAE 90.1, 2019, energy use of buildings has been cut in half if it's built to the standard. So that's very significant. We've made big progress. Try and think about other industries that have made that progress, have doubled their efficiency over that time period. Very few. So we should be proud of that. And 90.1 2022 is meant to be published in probably in a matter of weeks, and that's coming out, and it's going to have another significant step, probably at least another 5% drop there as we move forward. What about the windows? We see a similar trend in the stringency. This is just showing the U factors for fixed windows as an example in ASHRAE 90.1, and you can see over the last 15 years, depending on your climate zone, they've dropped by 20 to 60%. And that big jump you see is going from single to double glazing that happened back in the early kind of mid 2000s in the South, and And so we continue to see U factors dropping in commercial fenestration codes. Quick note, from other than those center glass numbers I mentioned earlier, everything in the codes are whole assembly numbers, including the framing, not just the center of the glass. So you have to look at the number for the combined assembly. So before we get in the codes, where they're heading, what they're doing, I found this as kind of an interesting exercise in a class I was teaching about what is fenestration and what is not in the energy code. And you would think it's obvious. You'd think common sense would say it's windows, doors, skylights. Yeah, that's fenestration. But what is fenestration in the codes? You kind of have to split it. And so there's this 60-degree angle. So if it's if that angle is more than 60 degrees, it's vertical fenestration. So that's going to be your windows and doors. And then less than 60 degrees, it's considered a skylight. And that includes unit skylights, as well as tubular daylighting devices, but also slope glazing is called a skylight under the energy codes. And it's all based on that angle. So those are some examples on the far right. There's a TDD, then you have kind of like these, that middle picture shows both unit skylights as well as kind of combo type skylights. And then in the middle there, that's both vertical fenestration on the top, but then you see that big sloped area that would be considered a skylight or slope glazing under the energy code when you're looking up your U factor. Over on the left, we all know kind of what vertical fenestration is, but I will draw out a distinction on doors. Not all doors are fenestration under the energy code, which sounds weird, but opaque doors, which means as less than 50% glass is an opaque door, and that's considered under the opaque criteria. Glazed doors have to have more than 50% glass, and then that does fall under the vertical fenestration. Now that angle is a little weird because a lot of you might be familiar with what's in the International Building Code. And they use a different angle than ASHRAE 90.1 or the IECC. And so you may have seen this 15-degree angle. So overhead glazing greater than 15 degrees from vertical must be laminated or have screens under the building code. Whereas the energy codes say use a 60-degree from horizontal, coming from the other direction. So really 30 degrees from vertical is considered a skylight. So it's a little different. It's a little confusing. If you look at that building in that picture, that's vertical fenestration in the energy code, but it's skylight or slope glazing in the building code, which sounds a little weird. But when you think about it, it sort of makes sense because it's for two different reasons. Energy efficiency and heat flow does flow, the heat flow transfer is a little different when it's sloped versus vertical, the way the convection works. Whereas the building code is focused on safety, like when do you have an overhead glazing hazard and when does that need to be laminated and so forth. So just be aware that they're two different purposes, two different angles when you're dealing with safety glazing and lamination or screens in the building code, as well versus what's considered a skylight in the energy code. Other interesting thing is, look at that building. Is that an all glass building? Yes and no. It's certainly it's all glass, but it's not all fenestration per the energy code. Spandrel area is treated as an opaque wall in the energy code. So, and you can see the arrows there kind of showing the vision area. The vertical fenestration is different than the spandrel area, which is not vertical fenestration under the energy code. So that looks like a 100% window to wall ratio building. It's not. It's about a 50% window to wall ratio building under the energy code, maybe a little more, 50 to 60%. And the opaque spandrel area must be insulated according to the R value table. That's the same as the wall requirements, or meet the opaque wall U factor, or use trade-offs. And just a side note, spandrel is not well addressed in the code. The U factors that you see in there are set for steel stud walls with a lot of continuous insulation on the exterior. It's not very realistic for spandrel. There is a research project going on right now that at the Charles Pankow Foundation with DOE support, where they're trying to better characterize spandrel, and that will hopefully enter into the codes at some point with more realistic numbers for spandrel. Otherwise, you need to look at the R value table or use trade-offs to comply. I'll side note there on this, I mentioned BIPV, building integrated photovoltaics. Spandrel is a great area to include that. There are technologies out there. You're not using it for daylight or view. go ahead and put some, get some energy production on the south side of the building, put BIPV in the spandrel area. So let's go into the codes a little bit. Energy codes, there's the ASHRAE 90.1, and then there's the International Energy Conservation Code. They are both developed separately, so sometimes there are differences, and but they, at least now, they're using the same climate zone map where we have these zones going from the far south. Climate zone 0, don't worry about, that's not in the US, that's in some parts of South America and the Middle East and Southeast Asia, but it doesn't occur in the US. Zone 1 is like the southern tip of Florida, and it's creeping into Texas, like Brownsville, Texas. Zone 2, is kind of like hitting the Gulf and a lot of Texas, and then it keeps numbering up. I'm in Wisconsin, I'm on the border between zone 5 and 6, and then it goes all the way up to zone 8 on the north slope of Alaska. And then when you go in the energy codes, you're going to see big ugly tables like this. And so don't worry about the exact numbers. It was asked in the chat, yes, these slides will be made available. And so this table will be in there where you can look up for your particular zone. So zone 4, that's like Baltimore or Kansas City. There are different U factors listed based on the energy code, whether, which version of ASHRAE 90.1 or which version of the IECC, and it's based on whether it's fixed or operable or entrance doors. So this is, there's tables like this, and it's a good point to note that all codes are local. So I'm talking about ASHRAE 90.1 and IECC as national model codes. They don't have any power till they're adopted at the local level, either by the state or even down at the city level. Where Denver has a very progressive energy code, but other parts of Colorado do not. And then some states are using ASHRAE 90.1 2010, and whereas other states are using 2019. So you need to know your version of your code and look and see what's being used for where the local project is. But I just highlighted one example where if you just look at that as an example, you can see how the U factors are coming down, an example of increased stringency. So roughly what do you need to do to meet those U factors? Again, this is a general guideline. Don't use this for code compliance, but it kind of gives you a rough idea of what's needed to meet the U factors. And you'll have this for your use later as well. And as you go from south to north, you're going to have to use more energy efficient features. So everything's going to be, double glazing, plus you got to do certain things to meet the solar heat gain in the south. So, but you can, zone 0 and 1, you can use pretty much double glazing, LowE to hit the solar heat gain. But then other than that, kind of do whatever you want. Getting into zone 2, you have to add a thermally broken frame, or you can use a thermally improved frame, not at the full thermal break if you also have argon in there instead. Getting into more of the center of the country, now you really do need a true thermal break. And then you start to add features. So zones 4, 5, 6, pick things off this pick list. So zone 5, Chicago, you have to have LowE glazing, a thermally broken frame, and then pick 2 things off that list. Could be argon and warm edge spacer, could be argon and a higher performance frame. Could be 2 LowE coatings as one of your choices there. You have fourth surface, room surface. So you have some flexibility, but if you pick 2 things off that list, you'll generally comply in that zone. So that's kind of where things are going. Then you go to the far north, you can keep throwing on more of these features. And in theory, zone 7, you can still do in double glazing, but more likely at zone 7 and 8, you're going to be going into triple glazing. What about solar heat gain? They stayed the same for a long time with low solar heat gain in the south, generally around 0.25, and medium or high solar heat gain in the north, like around 0.4 to 0.45. That's changed a little bit with the latest energy codes, 2019 90.1 and 2021 IECC. They list 2 numbers, one for fixed, one for operable, just like there are separate U factors for fixed and operable, but don't let that panic you. It's the same glazing type. So even though it says like 0.25 and 0.23 in zone 3, that's actually the same glazing type. It's just accounting for the fact that the framing's different generally in a curtain wall versus a slider or something like that. It's really the same glazing type. The only real change is they're starting to require these newer, lower, next generation triple silvers with lower solar heat gain in zones 0 and 1. You also get credit for overhangs and sunshades. So these are the overall solar heat gain numbers, but you can do it with the glass, but you can also do it with sunshades, overhangs, things like that. So what's coming 90.1 2022, which I mentioned will be published, and you'll probably see some news releases on that in the coming weeks. There are new thermal bridging requirements. We'll talk about that. There's a new envelope backstop limiting how much envelope performance can be traded off in the performance path, although it's fairly flexible, at least the one going into ASHRAE 90.1. There's a new additional energy credits section, which is a way that they can use to advance the energy code, where it says meet the main energy code, meet the basic requirements, and then on top of that earn points. So this would be something that will involve choices for the architect and specifiers and designers out there, that you're going to have this big list. You're going to say, I need to earn 50 points for this type of building in this zone. And then you have a list of many options. You know, it could include different mechanical systems, you know, on-site renewable energy, tighter air leakage, better daylighting. And then the ones that affect, you know, the fenestration industry are really, you get extra points for going better than the base requirement for high performance fenestration, using shading, daylighting, on-site renewable energy, all are kind of in there as options. But that will be a new thing. ASHRAE is going to come out, and that same concept looks like we'll go into the IECC as well. ASHRAE and Pacific Northwest National Lab is kind of the champion of it, are developing training materials to help people with understanding and complying with those new requirements. There's also a new on-site renewable energy requirement, which I mentioned earlier, strongly pushing PV and BIPV on the building. And so there's certainly exceptions and you know, for when you can't do it and all that, but it's really trying to push the use of on-site renewable energy, usually solar, on the building in new buildings, and then newer, tighter air leakage requirements and increased testing. I mentioned thermal bridging. It's kind of new. I want to mention what I mean by that. Some of you may have heard about it. It's thermal bridging is, I'm not talking about like a thermal barrier or thermal bridge in the window frame. That's accounted for in the NFRC U factor already. I'm talking about the rest of the building where it's bypassing of insulation. So the most common areas are like parapets, balconies, brick shelf angles, things like that. So that Chicago building on the left is a famous example, beautiful building. But all those balconies, concrete slab edges just sticking out, are basically acting like radiator fins. And the IR image shows that you know, you can do balconies in a good way where they're separated from the environment. But in this particular case, they're just acting as radiator fins. So that's a thermal bridging to the max, and greatly affects the energy performance of that building. So from the fenestration standpoint, it's really affecting the details at the wall window interface. How do you install the window, and how do you, it's not really about installation, it's about the design. How do you design the details for that interface between the window and the wall? So this is something really for the designers to take a look at. It also affects sunshade attachment as well, because that's a potential penetration through the insulation. Now, a lot of you are already familiar with how do you control or draw the water and air lines when you're looking at a facade, and make sure you control that. It's the same idea, except now you're going to draw a thermal line where you're going to look at the continuity of the thermal line. Where are you breaking that up? And I'll show an example of that here in a second. But there's requirements now set in ASHRAE 90.1, and it's being proposed for IECC as well, although not fully decided yet, where climate requirements are set for zones 4 through 8. So the, you know, kind of the middle and the northern part of the country. I'll show some examples on the next page, but I did want to point out, and there's a QR code there, that NGA has developed a new design guide document to help, you know, with information about this, on how to address thermal bridging when it comes to that interface condition between a wall and a window. So take a look at that. But here's what I mean by controlling that thermal line. So just like you're probably used to looking at your water line and your air line, Here's two examples where they're really just trying to get, high level, so for instance, there's a little piece of metal flashing under there, yes, that technically is bypassing some things in there, but we're not going to worry about that for now. We really want to just get kind of the general alignment. So on the left there, that's what would be considered an efficient and compliant, well design detail, where you have everything is lined up. You have the glazing unit, the thermal break in the frame, and then the insulation all lined up. So there's really no major bypasses. And so that red line there is showing the so-called thermal line. Everything's aligned. In contrast, the one on the right, I don't know if this may not necessarily be a common building, but if they have a wall cavity where they're putting the insulation on the interior, and you could have good insulation, you could have a great good efficient window system. So here we have double glazing LowE and a good thermal break in there. The glazing, the thermal break are lined up, but the insulation's over on the other side. So on paper, you might think you have a good wall, you have a good window, great. But when you look at the detail, you see that where that diagonal line is, there is no insulation, nothing stopping heat flow at all. That's a big thermal bridge where you're going to lose a lot of heat out there. And why do you care? Yes, the energy efficiency, but why should you really care is you're going to get callbacks and complaints from the building owner, because you're going to get cold points, condensation, maybe even ice if you're up where I live. So that's the other reason, is if you're looking for cold points and trying to avoid those and adjusting your details, then you're probably already also taking care of the thermal bridging. And like I mentioned, this is more of an issue for the designers than the manufacturers, because it's about the details. But in general, what ASHRAE says is they're just keeping it very basic. Just align the glazing with the insulation layer. If you're doing a recessed window, wrap the insulation back. You can do you wrap it back up to the window, not under the window because you have structural issues, but back to the window. Or you can use a wood buck as another option, which we see sometimes in concrete buildings, where they'll have the opening there and then use a wood buck and then that the window goes into. But there's multiple ways you can do it. Or you can do a very detailed psi factor calculation. And they're doing this up in like Vancouver and to some degree in New York City and so forth, where you can do a psi factor as a way of, it's kind of similar to a U factor, but in a linear standpoint, looking at the interface condition. For sun state attachment, it's pretty easy. If you're going through the insulation, you can have as many point connections as you need for structural requirements. Each has to be less than 3 square inches if you're using carbon steel. So like if you're using those knife edge blades, if you're using carbon steel, it has to be less than 3 square inches. If that's not enough for you, go just change it to stainless steel and you can get up to 9 square inches, which is plenty. Lastly, I'm going to wrap up with existing buildings. We work very hard on new building technology and codes. That's everything we've just been talking about. Yet we're ignoring the vast amount of energy used in existing buildings. And DOE has estimated there's like 2 billion square feet of single pane glazing still out there in commercial buildings. And then on the residential side, there's like DOE estimates there's 47 million homes with single glazing still out there. A similar number of homes with less efficient double pane clear, meaning no LowE glass. So better than single pane, but still not what we would consider a efficient window out there. So to address this and increase focus on existing buildings, many locations, especially cities, are starting to enact building or have already enacted building energy disclosure laws. So this basically says, if you're building over a certain size in this city, you must publicly disclose your annual utility bills. And it's just simply from a transparency standpoint. Help identify your Energy Stars, help identify your energy hogs. Maybe that makes a difference when you go to sell that building or lease out that office space. So it's the first step. But many are now taking that next step towards what are being called building performance standards, which takes that disclosure and then sets actual limits, actually energy use limits and fines or taxes if you don't meet that. And they're expanding rapidly. So a lot of you may have heard about New York City Local Law 97, and that was one of probably the first example. But it's not just New York City. St. Louis, Boston, Washington State, District of Columbia, Colorado as an overall state level have all enacted these now. Starting dates, some of them use carbon limits, some of them use energy use limits. They start, roughly 2024 up to 2026. The fines are, they're coming, but building owners have already started planning because they have, as we know, even just doing a simple project commonly takes a year now, so minimum. So they have to start planning now if they want to beat some of these fines. And it's a large incentive to upgrade existing buildings. And of course, they're going to do things like lighting and mechanical, easy things first, where they can. But it also improves the economic retrofits, looking at and starting to look at the envelope, replacement glazing, replacement windows, secondary glazing, LowE storm windows on the residential and multifamily side, things like that. And if you see a dot here, this is expanding rapidly. Every location on this map has either enacted or a policy or has committed to passing a building performance policy by Earth Day 2024. So this is, if you're involved in retrofit and looking at that as an opportunity, either as a designer or a manufacturer or supplier, look to these locations first. It's a big opportunity. It's not just New York City, which everyone talks about, but it's going across the country like rapid fire. And so what's this mean? It's a great fenestration upgrades. There's great technology for replacement glazing. I mentioned vacuum glazing is one great option for historic, where you have single pane, but you can't change the window, but you want to change the glazing, go to vacuum glazing. Also just traditional, non-historic buildings. If you can get someone to upgrade their double glazing, replace it with a modern LowE, especially two LowE coatings, great, do that. You can even do replacement windows, but there's many cases where you can't do that. Rip out and replacement is either impractical or cost prohibitive, or maybe in historic buildings you're not allowed to, or the building owner doesn't want to replace those existing buildings. So everything shown on this screen are examples of upgrading the existing fenestration without replacing it. So this is commercial secondary windows, LowE storm windows, where they left the existing single pane glass, and then they mounted a LowE glazing either on the inside or outside. And some of these, like the left two, are not necessarily historic, but it was more cost prohibitive, or and so they chose to use these secondary glazing options. The two on the right are historic applications. The one on the lower right is in the Naval Academy, where they're using exterior. They had to match their famous seafoam green, so they can do custom colors. So they match the historic appearance, but now upgraded that with LowE exterior panels. And so here's some more examples. I kind of talked through the technology already. You can do operable or fixed options are available. So when you're doing multifamily and you want to have it, operable for natural ventilation, there are operable versions available. You can do interior or exterior. And then, depending on the case, the cost can be significantly less than a full window replacement. So the options are good, technologies available there for both window replacement glazing, and when you can't do those things or it's cost prohibitive, to look at these other options. Finally, I'll mention that it's improves the insulation, the thermal performance, but it's also an air sealing measure. I've been involved with some case studies where just doing the windows, nothing else in the building, no other air sealing, we decreased the overall building air leakage by 10%, which is significant when you're not even touching everything else in the building. And with that comes improved comfort, improved acoustics, and that's, many of these projects are actually doing it for the acoustics as well as the energy performance. So look at those options as well when you're dealing with the existing or especially historic buildings. And there is product information out there. EPA has an Energy Star program for exterior and interior storm windows, basically LowE storm windows. And they have information on their website. There's also the Attachment Energy Rating Council, has a new certification program for both storm windows and commercial secondary windows. So you can look for information there on some of these products as a new alternative. So that's what I had for today. I think, yep, we've gone about 45 minutes. So, and hopefully we'll have time for a little bit of Q&A. But just to recap the learning objectives, we kind of highlighted some of the new technology that's coming out, how fenestration is treated in the energy codes, some of the different features that are required to comply with the south versus the north of the country, how to deal with this thermal bridging requirement, which is coming up in some of the energy codes, and then some of the new considerations and opportunities there in existing buildings. So I have not looked at the chat or Q&A, so
Yeah, Tom, there are 2 questions in the chat, and then the rest are in the Q&A. Happy to read. First one in the chat is, on older buildings, are old out of production coatings available for selective replacement, or just off-the-shelf products only available for selective replacement?
Ooh, that's a good point. A lot of times buildings will inventory somewhere in the basement or somewhere, like some extra glazing for that reason, in case especially if they're using a custom coating or something like that. I don't have an answer for that. There are a wide range of tints and coatings with different appearances, both LowE coatings and reflective coatings. I would say the best option is speak to your glass company, your primary glass manufacturer, see what they have. There may be something that's a close match. I don't know that they really inventory things that are completely out of production, but I don't have a good answer. But you can, I would say consult with your glazing supplier and see what they say.
Okay. Another one that's up a little higher. When using dynamic glazing, is it the highest U factor SHGC values that are considered as far as the codes are concerned?
So ASHRAE 90.1, we did work to make sure that dynamic glazing is recognized in both the IECC and ASHRAE 90.1. ASHRAE 90.1 basically, well, I'll just make a general statement. In general, the codes say that they want it to be automated. They want it to be treated separately than static glazing, so you can't average between the two. But if you basically if you automate it and then you get credit for the dynamic performance. So over 90.1, they give you credit for the low solar heat gain. So if you're getting down to 0.09, they're giving you credit for that. In the prescriptive path, as long as it's automated. In the performance path, you would actually model the real controlled performance. If you have a certain algorithm that hour by hour through the year, work with your simulator who's doing that building performance model, and they can model that to take credit for that dynamic performance, where it's low when it needs to be low and high when it needs to be high. The IECC, they have a minimum dynamic ratio, which is they want to make sure that you have a certain range and ability, true dynamic performance, the ratio of high to low. But again, they both want it to be automated, and in that case, they generally will give you credit for the compliance. So I hope that answers that question. All right, let's see. Oh, then Q&A. Okay, so I see those. Thanks. Let's see. The first question I see is, to my knowledge, what studies have been done on dynamic glazing to assess occupant well-being, productivity while electrochromic glass is being used? I am not familiar with that. That's an interesting question. I know there's been some studies on, what level is needed to hit glare control, because glare is part of that you want the light in view, but you also, glare can also counteract some of the performance benefits in an office and so forth. And so I know electrochromic glass, that's one benefit, is if you have the proper range of performance, you can use it for glare control when that's a condition, and then open it up when it's not needed. A lot of those studies, so the comment is will decrease VT, natural lighting, impact the occupants. I don't know specifically, like if you ran it in the darkest state all the time, then maybe, but the whole point is you don't. The whole point is you're using it dynamically. And also a lot of those studies have to do with view as much as they do with daylighting. And so having access to quality views, including nature and motion and things on the outside, it sounds nebulous, but there are studies that show that that's the benefit, is from being able to see, and that's true. You still get, even at 10% visible light transmittance, you are still getting a view to the outside. But it's a good point. I haven't seen like specific studies about that in dynamic glazing. Some of the suppliers may be able to comment on that though. Next one I see is on BIPV. It's asking about efficiency of BIPV compared to like rooftop PV or conventional solar cells. I don't know the answer to that offhand. Maybe some suppliers could put something in the chat about that. In general, especially for the vision area, you're trying to find that balance between generating electricity using the UV part of the spectrum and the infrared and maybe a little bit of the visible, but also it's a window. You're still letting the light in for daylighting and view. So in that case, I think the vision area efficiency of BIPV is going to be less than like a rooftop for sure, but you also can do a lot more area of it. You can do your entire windows. So overall productivity may be better. But again, maybe as far as specific numbers, you may want to consult with some of the suppliers out there. Is there an added cost to the use of thermally broken aluminum for framing? Yes, but and we account for that when we set the requirements for ASHRAE 90.1 and IECC. We have to show certain cost effectiveness requirements. So when you see a U factor that in my slides basically says you have to have a thermally broken frame, basically zone 3 on up, then it's been proven to be cost effective. So I don't want to talk about numbers on a presentation like this, but it's less than you would think. So and it has been shown to be cost effective. And similar to thermal bridging, keep in mind there's a minimum edge distance for the anchors, so thermal break needs to be coordinated. Yes, that's true. ASHRAE 90.1, when they're looking at thermal breaching, they're really trying to just tackle the tough problems first, things like parapets and balconies. And for windows, they said, let's just keep it simple. We're going to ignore that flashing that may go under the window. We're going to ignore anchors for the fenestration. Just keep the glazing and the insulation lined up, because that takes care of maybe, it's the 80-20 approach to problems. You're trying to take care of the big thermal breaks. But that's a good point. In a detailed psi factor calculation, then you should look at the thermal bridging, both from the linear, but also anchors, which are like more point thermal breaks. Then you can do that. So it's a good consideration to include it all. But we're also just trying to keep it. It's a new concept to people, so 90.1 is trying to keep it somewhat simplified at this point. Air leakage. 90.1 has tighter air leakage requirements. How are moisture control requirements inside the building keeping up with a tighter building? Water vapor inside can be trapped and collect on interior glass surfaces. Yes, so it's ASHRAE 90.1 and the IECC, per their scope, is only looking at energy. And so they're only looking at the energy aspect of air leakage coming through, that you'll have to recondition cold air coming in or vice versa. It looks at both infiltration and exfiltration. They're looking at the energy aspect. But yes, it's understood that moisture travels with air. And so if you have poor air leakage control, you can potentially have moisture issues as well. But I would also say there's a lot of, there's a certain amount of humidity in buildings anyways, and that's more occupant driven, and especially in multifamily and residential type applications where you may have other things like plants and so forth. And so even if a perfectly airtight building, you can still have, moisture issues, not so much traps, but that's like temporary condensation, especially if you have cold points. So that's where, again, where thermal bridging, if you're a designer already used to looking for cold points, then you're hopefully addressing thermal bridging already. Because if you have a cold point, even with a perfectly airtight building, you're going to get some condensation or ice on that area. But yes, it's a good point. We kind of have to look at controlling all these aspects together. Curious, is it true that Inflation Reduction Act is applicable only for electrochromics? False. NGA, we gave Irma Lascelles, the technical director for NGA, and myself, we gave a presentation on at a high level, some of the things in the IRA. Electrochromics is in there, at least for a short time through like 2025, at a 30% credit, which is significant. And we believe IRS is issuing some interpretations or guidance on how to comply, what's required to comply with that. But electrochromics are in there, but so are just high performance glazing. If you meet 179D, which is the commercial buildings energy credit, has been greatly expanded. Significant, very significant a tax credit is available there now, and it's been expanded, so it applies both to private sector as well as nonprofits. They're trying to make it easier to use for existing buildings as well, so that would incentivize high performance glazing of all types. And there's also a ton in there about solar and BIPV as well, 30% credits. And every time I say 30%, it can actually even be more. It can be 40% if it's domestic content. It can be 50% if it's done in a low income qualified neighborhood. There's other credits like that. It can be very significant. Yes, electrochromics kind of made the news. That's in there, but there's also a lot more in there for high performance glazing and solar as well. And I encourage, I don't know if that old presentation we did a month or two ago is online or not, but it might be. If so, maybe staff can put it in the chat. I don't know, or later. And then last one I see is, I believe, there's some more. I believe most vision area BIPV is more like 5 to 10% efficient, whereas PV in a solar cell can be 20%. And I know like 18 to 20%. Yeah, that sounds probably right to me. But again, I see that's Kyle. I assume that's our good friend Kyle at NSG, but who is a guy who would know. But and then the main point in my mind is that the advantage is, even if the efficiency is a little lower, you have so much more area you can do on a building in the vision area, in the spandrel area, than you can on a rooftop, especially in a tall building. So it's makes up for it a lot. And I think that's all we have. So.
Excellent. Well, thank you for your time, and thank you everybody for attending. We hope you enjoyed the session. With what's on the screen, NGA, with its 70 plus volunteers, has produced over 90 glass technical papers on a variety of topics that are free to download, as well as 3 design guides and 15 manuals. But we provided links to a few that were relevant to today's presentation. We'll also put those in the chat. And so we encourage you to visit glass.org to browse even more of our technical information that's available to you. And I will put those in the chat as we speak. And then thank you for attending. As noted also in the chat, this recording will be posted within 24 hours to the glass.org/on-demand webinars page. We wish you the best for the season and in the new year. We appreciate your support and participation in our initiatives, and that helps make webinars like today possible and keeps advocacy for glazing and glass building products at the forefront of our mission. We look forward to seeing you in 2023 at a future NGA event. Have a good afternoon.